All right. We're going to do the example problems. So go back to page 700. At the bottom it says resultant vectors. Vectors arise in many applications. Velocity vectors and force vectors are two that we will discuss. For example, suppose that you are at the beach and think that you are swimming straight out at a certain speed, which is a magnitude and a direction. This is your apparent velocity with respect to the water. After a few minutes, you turn around to look at the shore, and you are further out than you thought and appear to have drifted down the beach. This is because of the current of the water. When the current velocity and the apparent velocity are added together, the result is the actual or resultant velocity. So let's say this is the beach, and this is the ocean, okay? And let's say that there's a buoy out in the ocean, and you want to swim to it. Here you are. So you start swimming in this direction. But the water current is going in this direction. So if you add those two vectors together, you're actually swimming in that direction. And you're swimming slower than you think you are. You're swimming slower than the speed that you're working at, right? So let's say you're swimming at 2 miles per hour, okay? And then this is 1 mile per hour. Well, how fast are you actually traveling? Well, that's a vector question. This would have length of 2, and this would have length of 1. What is this length here? You'd have to use trig to figure that out, which is what we're going to do. So, example 6. That's kind of creepy. Oh, wrong button. Okay. So, here we have a boat that is traveling 25 miles an hour straight east. And then the water, or the wind, I'm not sure which one it is. River. The river is moving 10 miles an hour straight north. How fast is the boat traveling? And in what direction is it traveling? And notice they've helped us out, and they have put this in quadrant 1. Okay. So how do we figure out what theta is? Inverse tangent of 10/25. So the inverse tangent of 10/25 gives us an angle of 21.8 degrees. That is my direction. Okay. How do I figure out the velocity of this? Cosine of 21.8 equals 25 over h. Is this a multiplier or a switch? Switch. So 25 divided by the cosine of 21.8. And we're actually traveling at 26.92 miles per hour. Why? Why is that? So we're traveling 25 miles per hour in that direction, which means that I will travel 25 miles in an hour. But the current is also moving the boat. And in that same hour, the current is going to move the boat 10 miles in that direction. Which means in an hour, the boat will travel from here to here, which is a distance of 26.92 miles. And that is the amount of, that's the distance traveled in 1 hour, which is the magnitude of that vector. Now, I didn't actually have to do this. What else could I have done? I could have done the Pythagorean theorem. It wouldn't have given me the angle. But if I wanted the velocity, I could use the Pythagorean theorem. Okay. What if the triangle is not a right triangle? Like the next problem. Um, something's not right. Let's try that again. There we go. Nope. So the boat is traveling 100 degrees east of straight north. So this would be straight north. I have my choice of doing degrees east or degrees west. Degrees west would rotate this way. Degrees east would rotate that way. So 100 degrees east of north, which means the boat is traveling this direction at 30 miles per hour. Yeah, we'll get that. Well, it turns out you'll see. And then the boat is traveling in that direction, but what is this one? Wind? The current of the water. So the water is traveling 15 miles per hour in that direction. So even though the boat is aimed this way, it's traveling that way. Right? It's pointed in one direction, but it's actually traveling in a different direction. And that's why riptides are so dangerous, because if you don't understand vectors, you could be swimming in a direction that's going to lead you out to sea. So it's kind of dangerous. Um, when I was in San Francisco a couple months ago, we rented bikes and rode it across the Golden Gate Bridge, and the tide was going out underneath the bridge out to sea, and the wind was also blowing in that same direction. And it was a Saturday morning. There were probably 60 or 80 small sailboats that had gone out under the bridge, and they were trying to come back, and they were having a hard time. So you had the bridge, and they all went under the bridge this way, and the wind was kind of coming in this direction. So they were all hugging this line and trying to break free. And once they made it to here, then they could go back to San Francisco. But we watched them for like an hour, and some of the sailors were really, really good. And you can sail into the wind, sort of, if you know what you're doing. But there were 80 sailboats bunched up right here that couldn't make it back into the bay because they were fighting the tide and the wind. So, all right. Um, what I want to know is, what is the length of that vector? Right? I don't have a right triangle. I have an angle. Now, what three-letter combination am I looking at here? Angle, side, side, which is the hard one, right? This one's not, because so angle, side, side. This is the pivot. Do you remember that? And the second one, when the second one rotates around, it's bigger than the first one, so it's only one triangle. Right? This is so long that when I rotate it around, it's going to miss. But if you had something like this, 9 and 8, when this flips around, it hits there. And then you have two triangles. But what if this is like 2? When it swings, it never hits at all. So angle side side is harder, but in this case, it's easy because 30 is bigger than 15. Yeah, when we did the law of sines. So this is a law of sines problem. So the sine of 22 over, help me out, sine of 22 over 30 is equal to I'm doing the law of sines. Sine of A over A, sine of B over B. So the sine of A over 15. So 15 sine 22 over 30. 15 sine 22 over 30. That's a good number. Why? It's less than 1. So now I invert the sign. Well, you can't actually do 100 minus 90 because it's not, this is not a 90-degree angle. So that this angle is not 10. Yeah. Oh, oh, I see. So 22 is not the, okay. It does look like it, doesn't it? Sorry. All right. Um so if I take this angle here and I move it over there, then I do know how big this angle is. It's 100 minus 22. Does everybody get that? 78. So this angle is 78, which means that this angle is 180 minus 78, 102. Okay. Okay, now, so now this is 102, and now it is side angle side, which is easier than angle side side. Thanks for picking that up. I didn't read the question. Side angle side, do we use cosines or sines? Cosines. When do you use cosines? Side angle side, side side side. And then the other three you use sines. Angle angle side, angle, and angle side side. Well, if you forget, it's okay. Let's try to do sines here. The sine of 102 over x is equal to the sine of 30 over that. It doesn't work. We don't have that angle. And if I tried the other side, it won't work. So if you're not sure which one to use, it's okay, because if you try the wrong one, you won't have the right information. The only thing you really need to remember is don't do law of cosines if it's angle side side. It's doable, but that you usually end up with a nasty quadratic that isn't factorable. So we kind of avoid those. All right, so this is 102. Let's call this A. So this is little a. Little a squared is equal to, remember the law of cosines? No. Yeah, I don't. It's. I do. I'll get those up on the wall. Yeah. Yeah, it's basically the Pythagorean theorem. The only difference is this piece minus 2 times 15 times 30 times the cosine of 102. And remember, the law of cosines is determined by the angle. The angle tells you which formula to use, whether you do the A, the B, or the C formula. Okay? So 15 squared plus 30 squared minus 2 times 15 times 30 times the cosine of 102. And that is actually A squared. I'm going to raise it to the 1/2, and I get 36. What does that mean? The boat is traveling 36.2 miles per hour in that direction. Mm-hmm. Yep, that is the magnitude. Okay. Example 8, finding equilibrium. How about I read the problem this time so I don't get confused? So, the story says, a skier is being pulled up a slope by a handle lift. Let F1 represent the vertical force due to gravity, and F2 represent the force of the skier pushing against the side of the mountain at an angle of 35 degrees to the horizontal. If the weight of the skier is 145 pounds, that is, the magnitude of F1 is 145, find the magnitude of the equilibrium force required to hold the skier in place. So, gravity is forcing the skier straight down, right? And then it's kind of like a ski lift that you just hold on to. The ski lift is pulling him that way, but he is being pulled up the mountain, right? So his weight is not only going down, but um, he is being forced against the mountain at a certain weight. Okay. So how hard does the rope need to pull in order to keep him from sliding down the hill? It's not going to take him up the hill. It's the equilibrium force. Where is the balance? So it wants to know, how hard does the rope need to pull in order to keep the skier in the same place? If it pulls too hard, what will happen? He goes up the hill. If it doesn't pull hard enough, he slides down the hill. And then, of course, assume that the side of the mountain is a frictionless surface. Because, yeah, ideal. We like to deal with the ideal. Okay, so the angle between the vectors F1 and F2 is 35 degrees. Okay, so we have the measure between F1 and F2 is 35 degrees. The magnitude of the F3 vector is the force required to hold the skier in place. So this is 35 degrees, and we want to know the magnitude of F3. Okay, well, this is a right angle, which means that this is 55 degrees. And then we know that the sine of 35, so let's call this theta, the sine of 35 is F3 over F1. So the magnitude of F1 is 145. So this is 145 pounds. That's the force. So this is 145 because that's his weight. So the sine of 35 is F3 over 145. We just multiply by 145 and we get 83 pounds. What does that mean? The rope has to have 83 pounds of force on it to keep the skier in place. That will prevent him from falling down the mountain. All right. Let's do example 9. Resultant forces. That's not very... A barge runs aground outside the channel. A single tugboat cannot generate enough force to pull the barge off the sandbar. A second tugboat comes to assist. The following diagram illustrates the two force vectors, F1 and F2, from the tugboats. What is the resultant force of the two tugboats? Well, first off, why would the tugboats be pulling in two different directions? Well, they do want the boat to go straight, but why don't they both pull in that direction? They'd hit each other, or one would be on top of the chain of the other one. So they can't pull straight. Well, what if, let me get rid of this. I don't need that picture. So here's the stuck boat. What if they just parked out here and then they both traveled in that direction? Would that work? No, they would swing together and hit each other. So in order to avoid each other or each other's chain, they have to pull in different directions. Okay? And I think they're two different sizes of boats. One can pull 15,000 pounds, and the other can pull 18,000 pounds. And then the angle here is 20. So what we want to know is how hard is the boat going to be traveling in that direction? How do we do it? Well, it's kind of a side angle side. Yeah, there are two different triangles, so we need to make one. So what I'm going to do is take this tugboat and move it up there, right? And then the end result is actually, this. Why is that line not parallel to the ground? The bottom tugboat is pulling harder. Does everybody see that? Okay. So now we know that this is 18,000, but we don't have any of the angles. It's not going to be 10. It's actually going to be a little bit bigger than 10. Right? How do you... Oh, I see. Okay. So this is 80, and this is 80. Okay, so that helps. So if I draw a parallel line right here, then this angle, well, maybe they're going to do it in a smarter way for me. So that's going to be 100, because these two have to add up to 180 because we have parallel lines. And this angle here has to be, it's also 100. Because this is 80. So this is 100, this is 80, and this is 80. So now, okay, let me do that again. I really confused you guys. I'm sorry. Okay, this is 80, and this is 80. So if I draw a parallel line, these are alternate interior, so they're equal. Right? Okay, and then this angle and this angle match, because this line and this line are parallel. So that's also 80. So we're just going to turn that into 160, and then this is 15,000, and this is 18,000. And what do I want? I want the length of this. Am I going to use sines or cosines? Cosines. If I try to do sines, it won't work. The sine of 160 over this is equal to the sine of this over that. There are two unknowns, so that won't work. So I'm going to do, let's call this C. c squared equals 15 squared plus 18 squared minus 2 times 15 times 18 times the cosine of 160. And then what will I do with my answer? Add 3 zeros, right. So 15 squared plus 18 squared minus 15 times 18 times 2 times the cosine of 160. Thanks for that. Now I need to times that by 1,000. And then take the square root. And I get something. That's not right. What did I do wrong? Oh, I can't do the shortcut because of the cosine. No, that should still work. No. 15, yeah, my shortcut didn't work. Plus 18. Yeah, I took off the zeros, won't work because I'm squaring. Minus 2 times 15,000 times 18,000. Oh, thank you. Times the cosine of 160. Yeah, the squareds got in my way. No, wait a minute. That's the same number. Oh, no, it's not. Yeah, it's the right digits, but it was the wrong place value. Okay, 32,000. What does that mean? Well, no, on one side it would be 1,000 squared, and the other side it wouldn't. It didn't work. So what does that mean? So one boat is pulling this direction 18,000 pounds, and the other boat is pulling 15,000, and the end result is we're going this way at 32,502. But wait a minute, that's smaller than 15 plus 18. Right, they are kind of pulling against each other. Now, what would happen? So this is pulling at 15, and this is pulling at 18, which added together is 33, but it's only going this way at 32. What if I were to make that 20 degrees smaller? Then this number would approach 32, right, or 33, sorry. What if I made the angle wider? Then this is going to get smaller until eventually it would be 0, at which point the two tugboats. Oh, you're right. It wouldn't be 0. It it would eventually, if we pulled this way at 15 and this way at 18, we'd be going this way at 3. But unsticking it heading to east would be 0. Okay, and that's how vectors work. So, well, we'll get more into that later. All right, you have a bunch of story problems to do. Give them each a try, and then tomorrow I will answer any question you have before we move on to the next section.